Okay. As I told you, we are almost at the end of the course. Today, it could be that we almost conclude, and then we have, as I told you, another lecture after next week uh, to eventually to conclude what remained or to discuss a little bit some particular aspects and to discuss together the tasks, which I will send you I would like to say in the next days or not later than at the beginning of next week, let me say Tuesday instead of the lecture. So you can look at the task, you can try to figure out what the project is. The project is to answer this question. And then during the last lecture after next week, we can discuss also these aspects in detail. Okay, last week, let me share now the presentation. I introduced the model predictive control. You remember very quickly, we have basically the combination. Let me use this word. The combination between the modeling here is indicating with the word detail, process, understanding, modeling. And then this intelligent part or the intelligent use of model control systems is the optimization, because we have an optimal control strategy. Basically, do you remember? Let me comment just this picture here. We have a target to be tracked. Could be just in a constant, a set point target, or there could be a trajectory, profile. We can see here these blue points. Do you remember? Last time I told you we are in the presence of we are speaking about discrete sliding mode control. Basically, the sliding mode control is discrete. Yeah, and the idea is to track, for instance, these blue points, having a prediction of this blue point, the y points, and the prediction is characterized by y hat through the model. And the idea is to predict through a prediction horizon and to generate a controller which is characterized by the controlled horizon. These horizons can be also different, but in any case, a prediction horizon is larger or equal to the control horizon. Yeah, in this course, for sake of brevity, we will consider the same length, which is the most used approach. We can see here, for instance, in the lower part of the picture, this u, which is a manipulated variable, the results or the result. I'm speaking about plural results because it's in a vector with more than one component. But let me go a little bit faster. This is basically the a possible scheme which allows to interpret how we can figure out this new control. We have a plane with disturbances eventually. We measure something. Using the model we predict, we can use the input, of course. In any case, we can use the output which we want to, which we have at a disposition, which we have at a disposition. To be more precise, we need to know the whole state. We need, in general, to know the whole state. Therefore, we need an observer if we cannot measure all states. We will say this later. Through the model, we have a prediction. And then the controller is in a particular control, in this case, because it's an optimal control, in which we have to optimize, do you remember, a cost function. Yeah, in order to explain the method, do you remember I introduced this, probably I used also in the past, I don't remember in this course, it could be. But anyway, we can see here, these two equations represent a motor, an electrical motor, in which the first equation, if I don't consider this Ka apostrophe multiply omega, is basically an RL circuit. If you consider this component here, this is basically the induced voltage which we have because of the movement of the rotor. We can see that the second equation is the mechanical equation which states the movement of the rotor. Km apostrophe and Ke apostrophe, they are equal, at least ideally. Apostrophe in some notation indicates that is radian per second and not round per second or round per minute. This K apostrophe, or the K, characterizes the motor. We can recognize here exactly the mechanical equation in which the input of the mechanical equation is the current. Of course, the current is generated by the voltage in input. We can see it from the scale. Last time I told you a little bit more in detail, but anyway, in our case, we needed a model to explain the model predictive control because the model characterizes the model predictive control. This again, this Ke apostrophe is the reaction, the induced voltage is the reaction of the movement of the rotor in the circuit. And Km apostrophe, which is equal Ke apostrophe, ideally, multiply the current, in this case, is the torque, the motoric torque, generated by the current in the rotor, of course, because of the presence of the magnetic field. Here, we can rewrite everything in terms of matrices. I did this exercise many times. Here, I don't need to comment because it's a block diagram which you have seen, I think, in the past, but it's not the focus of this lecture here. Now, I am copying again the equation 1 and equation 2, and I apply the Forward-Euler discretization. The Forward-Euler discretization, in which Ts is the sample time, which I haven't considered in the system. About the Forward-Euler, I already told you a lot. Remember, in the session dedicated to the discrete system. Yeah, this means if I plug in this position on the lower part of the slide, I will obtain equation 1a dot and the equation 2a dot. Believe me, last time, probably I told you a little bit more, but we are able to do that to understand the meaning. I realized from here to here, I rewrite everything in terms of matrices. This exercise we did many times. And look, the output, which I would like to control, is the second variable. We can see here from the matrix C01, this in our case is the omega, the velocity, because the first state, you remember yesterday I told you, but we can see directly from here, equation 1 and equation 2, the first state is the current, the second is omega. You can see also from the discrete. I can write this expression here in general form, in this form here, which we have AK, BK, as this we can see we have here the representation of matrix in form of discrete. Do you remember I told matrix AK and BK, or CK, even though CK does not change, because the output matrix is not a dynamic matrix. Oh, excuse me, it's not a dynamic equation. This means the matrix does not change in the sense remains 0, 1. No? CK remains 0, 1. Here we can see that the matrix AC and the matrix AK and the matrix BK is different. They are different with respect to this matrix here. We can see the presence of an important element, 1 minus, but the important element is TS. In any case, are different. Also here TS. I should remark that TS plays an important role because if TS is too small, remember I told you we fell down or we end up in not controllable, because if TS is very small, we don't have that possibility to control the system in its representation, in the microcontrol. This means we cannot use, or almost not controllable if TS is too small. And here, if TS is too small, again, we lose not only the controllability, but also the observability. About the observability, I will tell you later. Why that? Because we have here 0, we have here 0, we have here 0. We have basically, we collapse in identity matrix, and we will see later that if in the presence of identity matrix, the system is not controllable. This means, it's not controllable, but is also not observable. I mean, it's not controllable if I have just one input, but the controllability basically we lose from here. But also the observability, I will tell you about the observability later, a little bit intuitively. We can demonstrate that the system is not connected, and then measuring a part of the state, I cannot observe the rest of the state. I can write in this form here, starting from 0, for instance, because very often this is the normal, the standard representation. I increase 1 here and 1 here, and then I start from 0, but the representation is the same. I compact it symbolically. Yeah, this is again the representation. Look, in this slide, you remember last time I told you a lot about the prediction. Also in this form here at the beginning, we have the prediction, because we can see that starting from today, K is today, state of today, input of today, I will predict the state of tomorrow. And also here, if I want just one part of the state, if I want to control just one part of the state, for instance, as I told you, the second state, omega, is enough to multiply the predicted state by Ck, and I will obtain the output. Now, I can predict also more step ahead, to remember. And recursively, if you remember last time, I can achieve my goal when I fixed the horizon, the length of the horizon, P. I can obtain the prediction until P, just plugging in each time the new predicted value. We can see from here, for instance, why this expression here, because instead of this variable here, we'll put this right part of the first equation. This means Ck Ak multiply Xk plus Ck Bk multiply your input. No? Instead of this expression, I have this one. And then if I increase 1, and then I will plug in everything in again, let me say, as before, I will obtain this expression, what I intend. If you write here +2, I have here +1, I have here +1. But x of k +1, we know where it is. We know where it is. It's this one. This means if I plug in this expression, believe me, last time I clarified it a bit better, we will obtain this. And so on until P. This is a more compact form of what we have at the beginning of this information, in which G consists of this matrix here, which is the matrix which multiply the state X, which F1 is this matrix here, which is the matrix which multiply everything which connected with inputs. U input of K, U capitalized input of K, is this vector here. Why that? It's exactly the element related to U input, which appeared here. We can see. I organized, let me say so colloquially, I organized everything in a vector. Column vector, no? Because, try to figure out, this is the first element, then we have the second element, this is the P element of a column vector. Yeah, and the matrix F1 is everything which multiply by the column vector, give back, let me say, the part related to the inputs. If you do here row multiply column, in which the column, this one, we can see at the transposition. We can see at the transposition. We will obtain from the first row, multiply this column, this element here, because the rest is everything zero. And then if you try to do again row multiply column, you will obtain the second row and so on. For G multiply X is a little bit easier because we can see that we can organize in a column C multiply CK multiply AK, CK multiply A square, and so on, everything which multiply X. The idea is to find at each step this expression, which is the input starting from today, the actual input, until P, until the future P. But of course, each time I will recalculate because something could happen. In general, we have changes in the system, we have disturbances. We will see now a little bit with disturbances, even though I don't have time to go in depth on variations, but with the most important, let me say, structure, we can also control variations and also uncertainties. The uncertainties are a little bit more complicated because the uncertainties involved the model, and the model is involved in the prediction. I don't have time to go in depth also with the observer, but we will understand very well that we can conceive an observer also to estimate changes in the model, and of course to update also the model in order to predict. An observer, I will tell you just in a basic form of an observer, but observer is a concept, and roughly speaking, I will tell you a little bit of a more general observer. We can estimate not only states, but also parameters. This is the point, parameters of the model, and disturbances and so on. Even though the disturbance is not so critical because of the presence of the feedback, also this structure, this fundamental structure MPC can control or can achieve under some condition, or can achieve under some approximation our goal. The idea is to calculate this U vector, and of course at each step we apply the actual input, and then we recalculate at each time. How I can calculate? Minimizing this cost function, typical cost function. The cost function not necessarily is this one, could be also another one, but this is a classical cost function, the most important in the sense, because we can see that here we have basically a row of the error between what I want to obtain, why R is the goal. At the beginning, we called Y reference. Is our targets, is our points, which must be known in advance what I have to achieve. Y hat is the predicted through the model, exactly what I told you until now. This vector here is here. Is known because the model is known. Of course, if the model is not precise, we have an error in the prediction. Therefore, we have to update the model in case the model changes. Multiply, let me consider this Q equal 1. Multiply the column, the column of the error. Basically, we have here the sum of the error square over the prediction horizon. Plus, if you consider R equal 1, what? The sum of the input square. Basically, this cost function represents a compromise between what I want to attain and what I am able, or what I am available to spend to attain the goal. Of course, why this weighting philosophy, because for safety reason, in some cases, if R equals 0, in some cases, we have instability. Why that? Because if I don't care about the amplitude of the input to achieve the goal, it could be that the input is infinitely large or unacceptable large. Because, of course, think about if I have an motor, I cannot consider a feeding voltage 10,000 volts. I don't know if probably there is also a motor with this voltage. But anyway, if I have a small motor, it's not possible. This means very often it's a compromise. We try to renounce a little bit of the precision in order to don't broken down the system. If U is not sufficient, of course, the goal will not show totally reached. But anyway, the motor is saved. Yeah, here we see, as I told you last time, the error. No? Q and R are symmetric matrices, weight matrices. Just to understand a little bit better, I put here a system with horizon of 2 samples. Typically, for instance, Q1 is larger than Q2, but not necessarily. But I mean, I am more interested to minimize the error tomorrow, or tomorrow and then the step after today. That could be at the second microsecond of my horizon, no? Instead of later, because I'm more interested to minimize what happens close to my time horizon. Of course, it's just a concept. It's not necessarily so. I will discuss a little bit this now, but in any case, makes sense to look, or could make sense. In some cases, to look what happens tomorrow and forget what happens in 100 years. Even though sometimes some philosophical, let me say, yeah, futuristic, let me say, approach could consider more important what happens in 100 years instead of today. Anyway, this I don't want to go in depth on this. But in control, we have also this two possible strategies to point out more, to put more importance at tomorrow, let me say, instead of in the future, or vice versa. I mean, Q1 very large with respect to Q2 means that the priority is to minimize the error tomorrow. Because Q1 represents the weight of the prediction of tomorrow. Let's see. From here, no? K plus 1. K plus 1 was tomorrow, K is today. I mean, the prediction of the error of today start with the first component, which is tomorrow. R is basically the matrix R. The weight matrix R is quite similar, but sometimes we work on the contrary. I mean, R1 is less than R2. Why that? Because this could help us to stabilize the solution. I mean, when is the risk? Q1 larger than Q2, R1 larger than R2. This means I put total energy to minimize energy, means the input, no? Power in the input, U square. Anyway, the input. To minimize the error tomorrow without considering much what happens after tomorrow. But this could could, if I don't change over time, this philosophy could generate instability. I mean, to look at the error tomorrow is important, but in the meantime, and this is a strategy, consider R1 not larger than R2, because that could generate error, but smaller, large enough, but smaller. Because what is the risk? If R1, let me say, much larger than R2, typically, let me say to understand what I intend, if R2 is zero, almost zero, I don't care what happens after tomorrow. I care just what happens tomorrow in terms of energy and input. But this could generate instability because if I don't limit, let me say, after tomorrow, if I go ahead with this philosophy, if I don't change R1 and R2, of course, I will generate a trend which is unstable. If you do the calculations, which kind of calculation? The derivative of the cost function J, which is here, which was in general here, with respect to U input, is the vectorial derivative of this function here. Believe me, I don't want to be boring, no? Or to become boring at the end of the semester. If you do this calculation, which you can find here in the slide, I will obtain this unique solution. Because the problem in the convex one, you remember I told you last time a little bit about, very short, about the convexity of a problem. The problem here is convex because we have a convex function to be optimized, because it's a combination of two convex parts. This here, sum of the square, or even the weighted. But the weight matrix is a particular. You remember this? Q and R symmetric matrices. I don't want to go in depth here. I forgot to say in positive defined. And positive defined, therefore, I forgot to write. Therefore, is the cost function convex, because we have the sum of two convex parts. Also here, no, we have a U squared, the sum of the U squared over the prediction horizon. The solution is one. If I do this calculation, which I don't want to do exactly now. The rest of the lecture is characterized by some variations. I don't want to tell you about that because I would like to show you the simulation, which is the most important in this contest here. And then we will switch on the observer chapter. But we can see in case, for instance, over the horizon, you change really a few theoretically constant. This could happen if you have a very short horizon and the dynamics quite slow, and or a sample time very small. F1 collapsing, F1 tilde in this form. Then we have a different approach which is based on delta instead of U. This is the advantage here that we considered in this case also a pass value of U could be easy to be tuned. Tuned means to find matrix Q and R in order to have good results. Yeah, somehow I will try to find the solution with respect to delta here. Basically, we have an optimal delta, which is the difference between UK and UK minus 1. Very often, we have a smoother solution because we try to optimize not the amplitude, but the variation of the amplitude. Let me see if I doing again the calculation. if the calculation must be done after constructing these matrices, which came from the prediction. Now, do you remember how I told you the first case? Here, a little bit different, the matrices, but the way to calculate is the same. Let me see if I forgot to say something here. But I didn't apply this. Is this in the sense, is this enough to calculate or to copy the matrices and to put it in this solution, the solution of delta, related to delta. The advantage here is this in optimizing delta, we have a little bit more fine optimization because I optimize the differences, the slope. Let me see, I forgot to say something. Excuse me. Mm. It's more sensible, no? This sense. Somehow is a little bit more accurate. Also because I'm using also the past input each time. But anyway, for the majority of the dynamics, we can obtain really similar results with U. The variation which I told you at the beginning. The U variation is delta U. Here we have also the case in the presence of the disturbance. I don't want to, I would like to skip this part here because nevertheless we can manage the presence of the disturbance also without this extension. Of course, with this extension, we can reject, let me say, properly, very well, but of course, we have to know the disturbance. We have to know the disturbance, and to know the disturbance means to have an observer to estimate the disturbance somehow. Yeah. And not only disturbance here, and this solution is considered constant over the prediction horizon. This hypothesis is not so extremely conservative because very often, how possible to say, the disturbance, the variation of the disturbance is much less than the variation of the state in the sense. Could happen in the sense. Or for short horizon and very short TS, very often we consider nevertheless constant. Okay, let me open now MATLAB to simulate what? In order to clarify, because I told you many things. This. And we will see that nevertheless, we can control also a system with the disturbance, even though the disturbance is not there, even though the disturbance is not predicted. Please pay attention, the disturbance cannot be predicted as long as I don't estimate the disturbance. Okay, let me now go to MATLAB. Let me share. I will upload the simulation in any case. Let me share. Okay, I will upload in this sense. But of course, at the end, as I told you, as I promised you, the material, nevertheless, is everything is in WeCamp, including the exam text, but I will send you an email with all material. So we have two possibility, not to look at the my camp, yeah, we camp, excuse me. I am mixing because in Loifano we have my camp uh, and also Perimail. This means concerning the material, don't don't worry. This don't worry. Okay, let me show you what you will find. I hope I share. I didn't share. Let me share. You can find here let's do it again. CC, I will upload in a folder with the name CCU variant. We can see that you have other folder CC delta. You will have basically this folder here, but very important is, but basically we can recognize directly. This file here is Simulink file, which includes the function here inside. This file here, which is the function of the trajectory. Do you remember I told you we have to know the target? We have to know the trajectory in advance. Otherwise, I cannot reach if I don't know what I have to reach. And then the M file with the parameter of the motor. Let me open this one. Let me start on this. We can see CC motor, and then we have already seen such kind of files, which we have the parameter of the motor. This is a real motor. No? Before going ahead, please pay attention. I'm using here global because I'm using an interpreted file. It could be that you have an embedded file. This means you don't need this global because you can pass. I show you the parameters of the matrix directly through the function. With embedded, probably with your version easy, but this MATLAB here is totally readable from you. No, don't care about. Lower data trajectory, remember data trajectory is an M file, in which I saved, it's written here a little bit, I saved the vector of the time and a vector with the name vel underscore NA, which is the velocity which I want to track, is exactly my desired trajectory. We called y dot point or y hat, remember as a vector. This is the data of the motor, and then I organized everything in terms of matrices. This characterizes this matrix here, the dynamics of the motor. Then you have matrix B, the matrix C. You can look at the lecture in this sense. And look at this, nevertheless, I would like to clarify a little bit better. This 0, 1 is the velocity which I want to track for a given trajectory and using a prediction. I used this discretization. I didn't apply, do you remember this, the forward Euler, but because I would like to test this one. This is is the MATLAB function. This is the MATLAB function, which realizes the discretization. We have some options: forward Euler, backward Euler, or in and did you remember I told you here we have, if you don't put any option, we have the exact discretization. Do you remember? Z equal exponential function up to minus st over ts. Do you remember? All other discretizations represent approximations or variation of this. MATLAB realizes this, even though it's an approximation because it's based on an exponential function, which can be just approximated. Then I have the matrices. We can see here that I have more than the matrix which I need. I don't know if you remember, I need F1, I need G. But here you have F2, F3, F1, because this file is used, the same file later, for generate or to simulate variations of the Kalman filter, excuse me, of the MPC. At the end, the matrix Q and RW, which represents the weights. Represent the weight. Run the value. We can see that the value here on the right. Now, let me open Simulink. Let me wait. It's running, it's still running. In the meantime, I look for the data. Okay, let me share. It seems to be working. Yeah. One second, I lost. Oh, look at this. Here's the system, which we have seen also, I think, in other contexts, but if you want, I can go inside. The matrix A, B, C, D must be here. Let me share. You can see here the matrix AR is our matrix, which represents the dynamics of the system. Then we have a BR, and we have another vector, 0, 1, because is the vector of the input. Now, I'm not sure if this is exactly correct, because I have to divide, I think, by J. I don't know why I didn't put, probably the student asked me, do some changes. The reason is, do you remember the second I show you exactly why? First of all, this column here is in a column of the disturbance. I can consider a disturbance an input. Why that? Because you remember I told you that this method is nevertheless able to control somehow the system, even though in the presence of a disturbance, because it's characterized by a feedback. But of course, the disturbance uh, has its map an input, and the map, in this case, I'm considering a disturbance which is going through the second equation, no? The mechanical equation. Initial condition, I can put whatever I want, because basically also this is a known. The matrix D is characterized by dr, which is 0, 0 in the column. Another column 0, 0, because you remember the matrix D, this matrix D, no? At the same number of column as C, but the same number of rows, excuse me, as C, the same number of column as B. This B. Now we will clarify what I intended. Yeah, we can see we have here a disturbance. One what? One torque. as a network with joule equal 1. And the first component of the vector B here is two inputs is multiplied by uh, the output of the controller. No? This here is the output of the controller, which is here. Let me see if I can clarify a little bit better coming back to the lecture. Yeah, from here we can understand well. We can consider the plus or the minus. It could be better minus, but also plus. It doesn't matter. Network in terms of D disturbance, and everything is divided by J. Therefore, I put J. I had J, but I don't remember the student asked me to. I don't know if it's clear. Here I can consider minus 1 divided or outside beta minus 1 if the torque is 1, the disturbance torque, but let me say tau could be 1 minus 1 divided J, because J must divide everything. Let me write also here inside minus. But also it's not, the disturbance can work in both directions, plus and minus, but let me put minus. And as Neluat, understand what I intend. Hmm. Now, as I told you, I need typically both states, current and velocity, to predict, and through the prediction to calculate the solution, which you already calculated offline. Look here, UK minus 1 is disconnected because UK minus 1 is the element which we need for the second variation, which I don't tell you. Go here inside. We can see a little bit better the structure. It's not an embedded system. It's just an interpreted. Basically the same, but with the embedded, probably you are habit to work at embedded. Sometimes we avoid with embedded some strange structure. But anyway, current, which I measure, velocity, which I measure. Of course, if cannot measure both, or can measure just one, I have to observe the other one with an observer. Here I have the ramp discretized, which states my clock, my K, starting from 0, 1, and so on. And here UK minus 1, which I don't use. Here inside, you can find the name of the file which you can open in order to understand this U solution, no delta solution, no disturbance explicitly inside. Let me open this file. Where is MATLAB now? Here. If I open this file, and this file, the name is here, we can see the function here on the right, on the left, on the right, depending. Here's the function. In the embedded, you have this element here as a parameter here, or you can define here inside. Here we can see I redefined matrix Q and R. Do you remember we have in the initialization phase, because some student asked me what happens if R equals 0 and so on. If R equals 0, we have a very high input. It could happen that we have instability. This means we want to really reach the error equals 0 without considering how much I can spend. It could happen that if I spend more than which I have, I will have an instability. XA in the two states, current and velocity. I will also the old state. We will see why the old. This I don't use. This is the element, the fourth element of the max. Here's the first and the second element of the max. I don't know if you remember in Simulink, the first two elements was or the were current and velocity. If you want, I can come back. X1 and X2 in accordance of the organization of the state on this max. Here, I organize better the index. You remember T0 was the ramp. I divided T0 by Ts. I sum 1 because I would like to start from 1, and then I round. This means I don't consider the decimal. If you want, you can look at the help run round. Don't remember exactly, but I think it didn't consider the decimal. Yeah. Yeah. Uh, to the nearest integer. Yeah, basically under 5, under 0,50, starting from 5 is 1. Could be also organized better, no? This counter. I can take direct clock. Probably is better in MATLAB, but in the old version, we didn't have this. Anyway, then we have here my velocity, 2 steps, no, excuse me, 4 steps, prediction in advance. This element, you remember I told you, is in the MAT file. I saved with data, with real data, with simulated data, but they are saved. With the load, I will call this. And then we have the last one, the solution, because we have, in this case, an analytical solution. Is possible to calculate the unique solution which we have. The system of the problem is convex because we have a convex function and in this case, no constraints or no explicit constraint because the constraint is in the barrier of the cost function. And I will consider of this vector here, please pay attention, this is a vector. This is a vector. The first one, the first element. Okay, let me simulate a little bit. Let me start. We have also a disturbance. I show you, 1 second, I will show you the disturbance. We can see from here. Ready? Again, Let me see with you a disturbance, the torque, 1 joule. You can see that the system is not able to compensate the disturbance. We can increase Q, but of course it could have, in order to minimize the error, it could happen that we have instability. This means we will see that it's possible to control, but under some limitation. Let me increase a little bit Q. This means more power to the input. More weight to the error implies more power to the input. Why that? Because if you look here at the end, under some limitation, increasing Q, of course, we have in the numerator, let me say denominator. This means is unclear. Just in second, just in second. Excuse me again. Yeah, what we can do here to maximize the input in order to minimize the effect of the disturbance, to reduce RW, we did. Let me see. Oh no, this is an error in this sense. No, no, I have to just to replace RW here. Yeah, excuse me. It could be that there was, yeah, now, okay. To minimize RW and to maximize omega, excuse me, Q. Now let me restart again the simulation. Now it's correct. It's correct what I did. It was an error in the in the notation, because the weight is RW. Do you remember I told you also at the beginning in the M file? It's clear. Zero means let me. It's an exaggeration. Yeah, let me restart as before. 10 and 0. This zero means don't care. Don't care about the inputs, and we can see that this RW weights in the denominator. This means maximal power in input. Of course, we can nevertheless increase the maximal power, increasing Q, but this is a little bit not so effective as reducing RW, no? Because we have a saturation. Let me see if we have improvement. We can see a little bit. Now, let me increase Q. Nevertheless, we have a price. Let me show the price. If you look at the input, which is the output of the MPC, we can see the value. Let me share. 1,400 Newton, excuse me, Joule. The torque is in Joule. Sometimes I make mistakes because very often I work with a linear motor in which we have an input force. Here is a torque. Torque is a Joule. Moment. We can see 1,400 and here 200 minus 200. Let me now increase in Q. I don't share, but believe me, I increase in Q from 10 to 10,000. Let me see. Yeah, we are already in the saturation. Seems to be that I did increase, I am not increasing much. Let me see the results. As I told you, we can reduce the disturbance, but not totally. Look, if I reduce the disturbance, let me show what I intend. Of course, the system, even though don't know anything about the disturbance, will be reduced. Let me consider here instead of 1, let me write 0,01. Here we have a disturbance which is much less. Let me show you. Now it could be that we are able to control or to reject. Look, almost. Or let me say a little bit better. Yeah, we can see a little bit better. Of course, if I increase RW, I will reject not so good. But in any case, I will reduce the input. This means it's always a compromise. I mean, here we have this input. 160 and then so on. And the result is what I told you. We can also measure the result in terms of sum of the error square. But if this is not acceptable, what I can do, I have to coming back here. And for instance, I have to reduce this. Now we will see that the input will be less. This means the error will be large, or the larger. And this depends what is acceptable for us. could be acceptable, could be not acceptable. Yeah, we can see that does not change much the result because this, remember I told you we are in a saturation region for the input. Let me say so. Let me look at the input. I don't think so they change much, but it could be that reduce a little bit. Yeah. You remember before was 160, now it's less than 150, right? Let me see if I see well. Of course, if I try to reduce Q or increase in RW, we will reduce again the input. But of course, we increase the error. Let me show you. It depends what I want to do and what I have at disposition. Let's put here 10. Now we will see that simulating, the error will be larger and the input will be smaller. And then, of course, the compromise in between is what we typically we are looking for. But we are always in the region of, let me say, in a saturation. But we can see a little bit larger. Let me see the input. Yeah. I don't know if you see. Yeah, reduce. I don't know if we reduce this, but I think so. But it's not important the amplitude. Of course, it's important because if I exceed the threshold, it could be dangerous for the system. But more important is the energy of the input. You remember, the sum of the U square. This means I have to sum over the time the square of this input here. If you want, you can do at all. But anyway, this is the idea that we can realize intuitively that decreasing Q and increasing R, I will have a larger error, but less energy in input. But we have seen that we have the possibility to manage because we have a saturation like in which the error does not increase a lot, but decreases nevertheless, let me say, the input. The reason is that not all energy is going the movement because we have a resistance and so on. This means you can figure out that nevertheless reducing the input, I will remain with the same track error. Vice versa, increasing U and decreasing RW, we reduce the error, but we increase the energy. This means we increase the input. To be more precise, we have to speak about energy or power. This means we have to consider the input square, sum of the input square. But we have seen that we have the possibility to manage because it's not exactly the reduction, let me say, of of manipulating the weights. We manipulate in the same way error and input. The reason is the input is not totally going the output. No, it's going in the losses, the electrical losses and mechanical losses. This means we have a disbalance. Yeah, this means that we reduce more, let me say more, the losses than, let me say, the output. Okay, let me take a rest. We will see here at 3 o'clock with another topic. We will start with the observer. This is the material which I uploaded. And let me take a rest. I have to call. We haven't seen that somebody calls me all the time. We will see in 20 minutes, something like that. Thank you. Yeah, let me now start a new topic, but very important nevertheless, even though is how possible to say, think because I'm not able to organize myself. Even though it's a fundamental topic, in the fundamental means basic knowledge, basic knowledge. But anyway, when I was in Santa Barbara, I studied in Santa Barbara University, my PhD, the part of my PhD. My professor said to me, Professor Paden, uh, Paolo, we have to know very well the background, the the fundamentals. Once we understood the fundamental, we can also try to do something more advanced. That just makes sense. Seems to be in a trivial sentence, but sometimes lecturer, professors, they don't consider this. They don't consider this during the examination and ask something strange. In my opinion, the examinations, of course, the examination means also at different levels, no? Bachelor level, master level, PhD level. But anyway, focus at each level what is fundamental. No? Okay, but this is a different thing. Okay, let me switch on the lateral camera. Why now it doesn't work? Anyway, the topic is observer or observers. I have here in Loifana a course dedicated to a particular observer, Kalman filter or Kalman filters. Do you remember I told you observer, observers? Plural means because we have variations on this topic, and Kalman filter is an observer, and a particular observer, and inside the structure of the Kalman filter, we have many variations. Therefore, we speak about Kalman filters as observers. But today, I don't speak about the Kalman filter because Kalman filter here in a complicated structure, an observer, but extremely complicated. I will tell you an Lundberger observer, which is the first attempt, which is the basic, let me say, fundamental Kalman filter. Look, again, our system, which we have seen half hour before. Exactly our system. This means now we are familiar with this. I don't need to explain. Let me just say is as a motor or represent. If I say is a motor, it's strange because I don't see any motor here, but it's represent mathematically, physically, the model of an electrical motor, a rotational motor, because we have a rotor, we can see the inertia of the rotor, and so on. What I told you quickly before, which plays nevertheless an important role in the robotics, in automation. Why that? Because automation system moves, or the systems move thanks to motor, very often DC drive or synchron drive. In general, it's a simplification, a synchron drive in any case. And a DC drive is a synchron drive. In robotics, such kind of structure structures are present in the joints of the robot, in the actuating joint of the robots. This means to coming back to our original title of the course, automation and robotics control. No? This is of course in a part. Do you remember I told you when I told you about the inverse pendulum as a part of a Segway, you know? To move something, we need actuator in robotics, in automation. This is one of them. For us, it's a system which can be applied everywhere, but in particular, automation and robotics. Look, from here to here, I don't need now to let me a little bit better. No, 1 second. I don't need to clarify how I can transform this information to this one. We have seen many times. Now, again, let me consider exactly the problem as before. I would like to control the omega, but I cannot measure the omega. I can measure just the current. The idea is measuring the current, observe, estimate, let me say observe omega. Before, do you remember, I told you, assuming that I can have a disposition current and omega. And I would, measuring current and omega, I predict omega, I control omega using model predictive control. Now, more difficult. Assuming that I don't have the sensor of the current. Excuse me, I don't have the sensor of omega, but I have the sensor in terms of current. I can measure the voltage in input. This is always possible because nevertheless, if the system is controlled, the voltage is somehow possible to get from the microcontroller. I have this one, the input of the actuator, the input of the actuator. Yeah, I have current, and I have to estimate omega because I need current and omega to control omega. This is basically the form, the general form of a linear system. Let me consider now the discretization, forward Euler discretization. I told you many times. Now it makes sense to consider, to think about what I told you in the chapter of discretization. And very important, the derivative. Very important, the derivative. Forward Euler. This is backward Euler, which I don't want to use now, but can be nevertheless used. Do you remember? Backward. But I will use forward. This is characterizes these two positions characterize forward. The approximation of the derivative is the same, but the meaning of this is different. No? Again, this note x of k is equal to x of k multiplied ts. Inside the argument, we don't put ts. Forward Euler, going ahead with forward Euler. Do you remember I told you that presents some advantages forward Euler, but of course also some drawbacks. Therefore, we have the possibility to approximate the system using many approximating techniques. But in any case, if you go ahead with these calculations, we will obtain this expression here, which is the discretized or discretization of the linear system, or the general linear system, which I present, which we considered during the semester. We can see also from here a little bit to remember that not for each TS, this kind of discretization is stable. But you remember I told you the eigenvalue, do you remember the concept? The eigenvalue, we can come back also later. The eigenvalue of this matrix here, the magnitude of the eigenvalue must be less than 1 to be asymptotically stable. But depending on the S, not necessarily if the eigenvalue A continuous matrix, identity matrix plus the S multiply A has eigenvalues inside the unit cycle. I will tell you a little bit later. This means we have this drawback, the stability. We have the drawbacks that before, let me say, colloquially becomes unstable. It could be that if you have oscillations, the oscillation not always is positive behavior of a system. Depends what we want to do. This means this is a possible discretization. This is a possible discretization. in any case, could have also some drawbacks. The advantages is easy to implement in the sense. Also backward, even though in linear is not so difficult, but implies an inversion of a matrix. Inversion of a matrix is also numerically sometimes not always comfortable. In linear systems, backward Euler, for instance, is in a do you remember, explicit, it's implicit form. We need some simplification, approximation to obtain the model. But anyway, this is not exactly the topic of today. I told you a little bit during the discrete or the discretization lectures, but of course, it's a big topic in any case. Hmm? This is the property which I use Tn. Once I multiply by Ts, but we have already seen, I think. Identity matrix multiply I x k minus 1 is equal x of k minus 1. X is in a vector, is in a column vector. Hmm? At the end, to summarize everything, I have this form. This is the general form, as I told you, to summarize everything. K minus 1 is the actual value. K is the future one. Forward and backward or any kind of discretization allows to build the model. Look, what I'm doing here, I am doing exactly what I told you before. X of k equals identity matrix plus Ts multiply A, continuous matrix, multiply the vector of the state plus matrix B, multiply Ts, multiply U input, everything calculated at k minus 1. No, also here, k minus 1, because on the right part, we have the previous step. Explicit form. I told you, I think, during the chapter dedicated to the discrete. Doing some easy calculations based on the algebra of matrices, I will obtain this, in which I pointed out that explicitly this AD, discrete, sometimes AK, I used also AK, depends on the books, because the lecture came from some books or yeah, some documents in which we have a different notations, but working with different notation, in my opinion, is help to be flexible. Anyway, identity matrix plus Ts multiply A, I told you also before, equal my AD discretized matrix. Now, look at the definition of the observer. Or better to say, yeah, the observer, but this, of course, is the fundamental observer, the basic form of the observer. Kalman filter, for instance, or all, or almost all advanced observer all observers start from this form, almost all. Had characterized the observation or estimate. If you want, you can use the word estimation, even though estimation is more oriented to an optimal observer. Kalman filter is an optimal observer, in which an optimization technique is inside. But anyway, we can use, in my opinion, both words. Estimation of x hat, x is in a vector, no? Consists of current and velocity. AD, the discretized matrix, x hat of k minus 1 plus BD, the discrete of B, multiply U input of k minus 1, basically what we had before. But now I add LD multiply C, multiply the error, in which the error at the time k minus 1 consists of this form. What is minus what I am observing or estimating. A little bit abstract until now, but we will be more concrete in a few minutes. The idea here, the idea is to obtain an asymptotically stable converging observer. This means exactly something like that, in which the error of K is equal in a matrix, which depends on LD, which is a matrix in the sense, in our case, we have just one measurement is in a column, is in a column. Multiply C, multiply the error. Probably here is written, if you remember, because this slide came from another course. Let me see if I will be able to clarify a little bit better. Otherwise, I will open shortly a couple of slides in order to justify why I'm writing here, if you remember. At this moment, I will tell you colloquially, and then we will see where come this expression here uh, from the past lecture, which I didn't hold here in this course. In any case, it's intuitive to understand that the error of today, let me say today, is a function of the error of yesterday. And if you think what I told you in the chapter of the discrete system, that this matrix here must have eigenvalue, magnitude of the eigenvalue inside the unit cycle, it is enough to design LD, which guarantees that the eigenvalue of this matrix are in the eigenvalue in the sense the magnitude of the eigenvalue of this matrix are inside, or let me say the eigenvalue is not wrong, inside the unit cycle. Now the question is where this comes from. How we can justify from here that we have this expression for A of K or A of K minus 1, which we can see depends on AD, LD, and C. C is our 1, 0, matrix 1, 0. The row matrix 1, 0. Here is the column matrix, which consists of two elements, L11, L21, to be calculated such that the eigenvalue of this matrix here are inside the unit cycle. Let me see here. I don't have the demonstration, but let me show you at the beginning this equation here, and the demonstration of if this equation holds. I will show in 2 slides from another presentation. But assuming that this works in continuous time, you can see in continuous time. If I discretize this, now we will see later where this comes from. In continuous time, we don't have here any discrete elements. AD is not there. LD is not there. We have A and L, everything continuous because we have here the derivative over there. Let me plug in this expression here and this expression here, forward order. Again, if you do this calculation, I just plug it in, I have this one. I start doing this calculation. Always remember that the E of K minus 1, this is the column error, the error in the current, the error in the velocity, equals identity matrix of the E of K minus 1. I don't know if this is visible. And now, if this is visible, I can really justify this form here. Because here we can see, in any case, multiplied by identity matrix. This means I can put in evidence on the right, this is a column vector. This is a column vector. It consists of current and velocity. I put in evidence on the right. Remember, putting evidence on the right and putting evidence on the left in a matrix or vector is not the same. This remains as it is. And when this dynamics is stable when this dynamic is stable. Uh, I can write everything in this form. No? If this is AD, if this is AD, as I told you before, no? At the beginning of the slides, I can write everything in this form because I can put this column vector here in evidence on the right, and I have this. Again, now the final question is, and then we will see again the concept of the stability, which I already discussed. Very shortly, I will show you where this expression come from. Let me open really two slides of an old presentation, which I didn't tell you until now. It's not necessarily because it's the continuous observer, because we can think about what we have in discrete, we have also in continuous, or vice versa, of course. 1 second, I will take in a presentation very shortly. In order to justify where this expression come from. Basically, is an expression which can be very well we can demonstrate very well starting from continuous structures, because the observer could be also designed in continuous. Let me find the material. Found it. Let me give me 1 second to open it. Okay, let me share. 1 second. I have to go out from here. We can see that I have this. I hope that I share. In this lecture here, which is an introduction to the Kalman filter, but what I would like to show you is just the idea, not related to the Kalman filter, but to the observer. In fact, we can see this picture, exactly what I told you until now. We have a system, we have a controller. About the controller, we know everything. We have seen many control strategies. But it could be that I need something to control, which I don't have. The case of the MPC is clear. I need both current and velocity, but assuming that I have just the current, I can measure just the current. How I can proceed? I can measure just the current. I would like to also have information about the omega. Here is not an MPC, because an MPC needs both. It's not a control. But we can see that the idea is to measure just one of both and to estimate both, what I measure and what I don't measure. Very important, what I don't measure, of course. always the same example. Here we can see a little bit the concept of the observability of an observer. We can see intuitively that if I measure here the second variable, the system is not observable. Why that? The concept of observability means measure one of both, one of them, let me say, we can have information about both. But if I measure this, I have just information of this because we don't have a connection between x1 and x2. I have a connection between x2 and x1. If I measure x1, the system is observable because I have x1 and I have x2 through this connection. This really flesh out what is the observability. Here, it doesn't matter what I measure because you have the double connections. x1 is connected with x2 and x2 is connected with x1, just to fix the idea. Here we have a possible definition of the observability. It's related to the distinguishability in finite time of the output through the system output. I can distinguish between x1 and x2 in finite time from the output. It's a little bit theoretical, but can help to fix the idea. The test for the observability in linear case, this one. But we can understand very well without doing the demonstration. The reason is it depends of the map of the output, what I measure, but it depends also on the dynamics. We can see from here. Okay, it doesn't matter what I measure. C, the matrix C, doesn't matter if it's 1, 0 or the 0, 1, because the matrix A is in a matrix interconnected. But of course, we can say that depends on C, depends on A. We can see here, depends on C, depends on A. If I measure x1, it is observable. If I measure x2, it's not observable or not fully observable. By x2, I can observe because I measure. But it depends on both, on C and A. But in general, we have seen that depends on both C and A. This is the test, which is also in a theorem because in a necessary and sufficient condition for the observability. If the determinant of this matrix, or the better to say, of course, here it depends on how many variable I measure. Could be also more than one determinant, but this is a little bit more complex. Let me remain with one measurement. If the determinant is not zero, this means that this matrix full rank, the system is observable. And we have a necessary and sufficient condition. Therefore, sometimes this result, this test, is presented as theory. Similar consideration can be done for the controllability, no? But in this case, the depends of B. You remember, I told you very quickly, and of course, the depends of A. No? Depends of A. We have some similarity. If A is in a diagonal matrix, we don't have the observability, we don't have the controllability because the system is decoupled. The key point is to have connections. Here. Just to roughly speak. Here we have other definition about the time variant system. Here, I forgot to say it's time invariant system, but remain on this. Okay, let me look again at the structure of this observer in order to show you where this equation comes from. Look here, we have the system which is characterized by matrix A, matrix B, and matrix C. And we have an initial condition. Then we have the observer, exactly what I told you until now, but here is in continuous. You remember hat, instead of K, we have the derivative. You have X hat. It's exactly this expression here, assuming that I know perfectly the system. What is the meaning I know perfectly the system? The matrix A of the system, the real matrix A, the real is strange because matrix A is something which is in the model, but matrix A, or the parameter of the model, is are exactly known. This means I can build the matrix A and B and C for the system, and the same matrix is for the observer. I have to add this input, this is a signal, multiplied by L, which is in a column in case we have just one measurement, of what? Of the error. Remember, I introduced exactly now the error, what I is and what I am observing, what I am measuring, what I am observing. Very interesting here is the initial condition, because the initial condition is different. We can see. This makes also sense because we don't know, we never know the initial condition, the initial value of the energy of a system. And at the end, y hat, the estimation of the output, the c time, the estimation of x. Therefore, x hat. C is 1, 0 in our case. Look, if I do these easy calculations, this means subtracting the equation of the observer from the equation of the system, we obtain this. Here we have the observer. Here we have the system. Here we have the system, excuse me. The observer can be considered also here because y is c time of x and y hat, the c time of x hat. Again, if I do this minus this, I will obtain this. Clear, no? Then I can put in evidence here x hat. This means I can write here A, which multiply the error over time, in which the error is x of t minus x hat. Also here, I can say minus LC, multiply the error, which is x of t minus x hat of minus t. And of course, I told you this, no, this is the position. I can put in evidence on the right, this column of E of t to obtain this dynamics, which is dynamics of the error. Error in terms of current and velocity. This is in a column, is in a column. Look, this equation here came from this equation minus this. It's easy to see. Then this part here, I can see as an A matrix and multiply the error column vector, which is the current which I measure minus the current which I estimate. And the second component is omega, which I don't measure, minus omega hat, which I estimate. This means matrix A, which multiply the error column vector. Here I can say minus L multiply C, which multiply the error column vector. But if I put in evidence on the right the error column vector, I have A minus LC, everything in parentheses, which multiply the error column vector, exactly this. Of course, the initial condition of this differential equation is E of 0 equals x of 0 minus E hat of 0. Please pay attention here. It's in a system of equations of the differential equations. I know for the current, I know for the omega, but they are interconnected. Otherwise, the system is not observed or not fully observed. And here we have a vector of the error, current at times, the error of the current at time 0 and the error of the omega at time 0 equals something. Of course, this I don't know. X hat, I don't know. Because the estimation of x0. Better to say, x0, I don't know. And therefore, they are different with the value which I put on the observer, which is this one. Basically, we have an initial observer error. This one. Now we have seen where this equation comes from. And then, as I told you before, if I do the discretization of this, I don't want to repeat, but we will obtain this expression here. Of course, I have to put also the initial conditions, two initial conditions, the error initial condition, one for the current, one for the velocity. You remember this? When it's stable, better to say asymptotically stable, when we have this condition, the error at time k or a step time less than the error at step k minus 1. Or better to say exists in a k, some when, which implies, if you look at this equation, if you look at this equation, this expression here implies this. And I told you the norms of the magnitude of the eigenvalues of this matrix must be less than 1, or colloquially we say that the eigenvalues are inside the unit cycle. We speak about the magnitude. Why? You remember, because the eigenvalue can be also complex. This is written here. This is written. Now, please pay attention, and then we are almost ready. I will just add some theoretical considerations, and then we will simulate. Yeah, this is the expression of the discrete form of the observer. I told you where this comes from again, otherwise. You remember, this is the definition. It's characterized, if you want, is defined by, no? Basically, it's based on the model of the system, because AD and BD, they must be the same, or almost the same. In Kalman filter, we don't need that they are exactly the same. Plus an injection signal, which nevertheless in the feedback. Here we have the feedback. And somehow the observer is in control of the system, because here we have the feedback between what I am measuring and what I am observing. This means the system and the observer are strictly connected by the feedback. And this feedback allows to control the error and to control to zero the error, thanks to the matrix LD. I will show you. From here to here is clear, because basically, what is the idea? We have two inputs, this and this, this and this. Did you agree? Okay, we can see this in a further input. This means this remained here, and I can organize this matrix here, which is the matrix B in general, which consists of two columns, BT and LD, because I have to consider two contributions, the contribution of U, which will multiply by B, and the contribution of the error, which is multiplied by LD. This, of course, it appears a little bit arbitrarily, but we will see that is not exactly arbitrary in the sense we have the freedom to put this. But of course, we have to be careful to place the eigenvalue in a particular way. Here we know everything about that. Note that the forward-Euler discretization is not an intrinsically stable method. Remember this. This means that TS must guarantee that the norm, of the eigenvalues of AD are less than 1, norm of magnitude. Okay. And this is a little bit, again, the explanation. This is stable, but this cannot be necessarily stable. It depends on this. It's not so dramatic if it's unstable, because we can stabilize everything in the observer using LD. Why that? Because let me show you. 1 second. Assuming that this AD is not stable. Could happen. It could happen. But using LD, I can stabilize. AD is not stable because the magnitude of eigenvalues are outside of the unit cycle, but we use in LD, I can stabilize because at the end is extremely important that this satisfies at least the stability conditions. This means LD can nevertheless correct something which could appear problematic. But of course, if it is possible to choose TS in a suitable way, we have more freedom to choose LD. Now we will clarify what. Why I'm saying if I have the possibility to choose TS, because we have oscillations and we tend to no, instability if TS is large. If TS is large. And sometimes TS is large with respect to the dynamics of the system, time constant of the system. How possible to say it's not a suitable choice because of this reason, because of other reason, but the problem is sometimes TS large is due because we have to put inside this TS many calculations, many algorithms, model predictive control or different algorithms. And this is running inside the TS. This means not always it's possible to reduce. How much I can reduce? You remember I told you last time, if I reduce too much, let me say colloquially, too much, we lose the controllability because we annihilate a part of the matrix B, let me say, and not only we obtain also in a matrix A, which is diagonal, no connection. Do you remember the intuitive idea of the observability? Using connections, we can distinguish what happened in X1, what happened in X2. If you don't have connections, we have some problem. I introduced really colloquially the concept of the observability. More in depth on this part, and then we simulate. This we have seen exists in a K somewhere or somewhere we have this, which implies this. But we have a different problem. We have to calculate LD independent of this is stable or not, independent of the choice of TS, which guarantees this. If this is guarantees, this is automatically guarantees. Also vice versa, no? If this holds, also this one. Yeah, here just to remember what I told you about the Laplace transform, zeta transform. To remember this, I told you a lot about that. The relation between Z and S, which states the exact transformation. Interesting, the map, which we can build. This map here can be more concretely expressed here. This using Euler equation. No? I don't know if you remember this from math. Euler equation. This means we can really map everything in terms of sigma real power, in terms of omega, and so on. For instance, this point here, do you remember I told you also last time, this point here is the map of the minus infinite on the real axis. This segment here is the map of the real line or semi-line from here to infinite. This means here we don't have oscillation. Do you remember I told you about that? I told you about it. What about here? Here we have oscillations because represent the line which we are here and the horizontal to here. Let me say calculated at pi, if I remember well. because this -1 is mapped for sigma equals 0, and omega multiplied Ts equals 0. Better to say equal pi. Therefore, I told you pi. If this pi, sine of pi is 0, cosine of pi is -1. If you go up a pi or a minus pi, I have this point here. And then if I move here, in which we have oscillation, from here, I will go to 0. I don't know if it's clear because I go toward infinite parallel to this. And I can consider this element here, or that this segment, the map of all dynamics, or the dynamics characterized. Let me show you this. This means here is omega, because on the real axis we have just omega. I don't know if you remember in math. No? As I told you, pi divided Ts. Or omega equals minus pi divided Ts. But also 2 pi, 3 pi. Huh? Everything which is here 2 pi. No? 3 pi, scusi, 3 pi. Also here, no? Omega minus 3 pi divided Ts. Of course, we can map, and the map is in particular curves, every point. And we can put also, we can design, we can graph, nevertheless, the correspondence of different points here inside, just to show you a little bit. This means here we have oscillations. No? This is mapped here. One is here. And then it's going to 0 if this is going to infinity. This is a possible definition of a norm of this norm 2, which is the maximum eigenvalues, or the better to say the maximal norm 2, the eigenvalues. But anyway, this is a little bit more, because you remember the norm of a matrix must be defined, must be defined. Remember this. If you're working with forward, we have the approximation of the exact on first Taylor first order approximation if I use Euler, just to remember. Really, let me conclude now to analyze the tool with the exercise. Yeah, I will tell you just 3 slides, then we take a rest a little bit, and then we come back and we do an exercise. So really, we conclude the course today, but in any case, after next week, we will come back to repeat some aspects, to discuss the project, which I will send you not later than Tuesday next week. So we have a week time to download the material, to look at the exercise, at the topic. Let me, 3 slides. Let me say, yeah, I think 10 minutes, 50 minutes. Let me go more in depth on this, because please pay attention. Why I told you about this norm too, because this notation doesn't mean much. Norm of this, which kind of norm? But also, this is not exactly the topic of this course. But if you remember, the norm must be defined. A norm is an instrument to measure something. I mean, this is a possible definition in which the norm 2 represent the maximal norm of the magnitude of the maximal norm 2 of the eigenvalue. Norm 2 means real part square plus imaginary part square root. This is clear, no? And if I consider the maximal of this is the maximal norm of the matrix. The maximal eigenvalue, better to say the maximal norm 2 of the eigenvalue, or better to say the eigenvalue. Yeah, this is really too colloquially expressed. The norm 2 of the matrix is the maximal norm 2 of its eigenvalue. But let me more practical. This is a little bit too theoretical. Do you remember this concept here? Eigenvalues must be inside. This means, again, the maximal norm of the eigenvalue of a matrix must be inside. If the maximal norm of the eigenvalue must be inside, all eigenvalues are inside. Let me, so roughly speaking, say so. This means, let me calculate eigenvalues. Do you remember the eigenvalue of this matrix here is calculated by, I don't know if you remember in math, probably I already told you about that. But here is a little bit different the problem. Huh? This is the condition. A little bit different the problem because LD is unknown. And the sense is easier because if LD is unknown, I can place really the eigenvalue inside the cycle. Why that? Because I can fix my 2 eigenvalue in discrete form, considering what I told you until now. I can place here, I can place here if I want oscillation. I can place close to 0 if I want a very fast system. Because I can use also this correspondence. This means I can fix this as I want. I can calculate LD, which guarantees this independent of TS, or almost independent of TS, because TS is in a technical, in this sense, becomes in a technical condition. Sometimes we are constrained for microcontroller, for everything which I know. LD, as I told you, if the measurements which I have at disposition just one, consists of just one column, if I am measuring just the current, for instance. Now, this expression here, excuse me, this expression here can be written this. Why that? Lambda 0, 0, because we have this identity matrix multiply lambda. We have 2 states. Minus because we have this minus here. Then AD we calculated before. Do you remember? AD we calculated before. Minus, LD in a column, which multiply the matrix 1, 0, which is the matrix C, which maps the output or the state, better to say, which I measure. Measure the current, the first state, in accordance with our description of the model. This is basically the implementation, let me say, on this equation. Now, easy. This is exactly as I did before, the calculation of identity matrix minus, remember, TS, better to say exactly this, otherwise I have to write also here, which is identity matrix plus TS multiply A, is already here. Huh? Everything is calculated, TS is given. Let me go slowly. LD multiply C. Why is this? Because it's the matrix L11 first row, L21 first row multiply 1, 0. Is the matrix 2 times 2. Why that? Because in the product between the matrix 2 times 1, which multiply in a matrix 1 times 2. This is the product between LD multiply C. Why minus? There is an error. There is an error. Yeah, should be plus. Excuse me. Should be, yes. Minus, multiply minus is plus. Excuse me for that. Where this matrix come from? Come from here. This matrix minus this matrix here. It's not so difficult, no? Lambda minus 1 plus this. 0 plus this because of this minus, and so on. Here I have to correct plus. I have to correct plus. Lambda, do you remember? Excuse me, lambda minus 1 plus RT is divided L, no? Yeah. Minus 1 plus RTS divided L. Here we have just plus KE apostrophe TS divided L. And so on, believe me, no? Believe me. I have to correct here plus plus, I have it. I have to correct here, and I have to correct this multiply this minus, this multiply this. This means I have to put minus here. We will see that with the computer, you don't need to care about plus minus because as we have seen in other context, the calculations are done automatically. I have to fix 2 values for lambda, but very important with this. Of course, I can choose different positions depending what I want to obtain. Oscillation, oscillation, how fast. About how fast, do you remember? I did an example last time how we can think, how we can proceed to determine in continuous, of course, but in discrete is, let me say, the considerations are the same because I can consider this map. No? It's exactly what I did last time. I don't know if you remember. I did this example, considering this example in the sense this procedure in a different example, but with the same procedure, considering the map in forward. Remember, Z equal 1 plus STS or S equals Z minus 1 divided TS. And remember this. Look at the MATLAB file. Then in any case, we have a lambda 1 and we have a lambda 2. Very important inside this condition here. What we can do now, and MATLAB can help directly, I have to correct a little bit this was plus, this was plus, and this was minus. MATLAB can do this in a microsecond. using again the command place. Minus here and minus here. L21. No? Exactly what I told you, using the function place. LD can be calculated now using the function place, but please pay attention. P is the same, and the same, I mean, I fix to a vector with the lambda 1 and lambda 2 could be also complex, but attention at this condition. For both, for lambda 1 and lambda 2. Place of what? Not A, B, P, but now A D transposed, C transposed, and P, everything transposed is the solution. The solution transposed is clear because do you remember when we used place at the beginning of the semester to calculate K, but we calculated also last time, no? You remember? K is in a column, in a row, and D is in a column. This means this transposed is not for us, technically at least something new. Conceptually, nevertheless, is something interesting and new because look, we have here the transition matrix of the observer, transposed. We have here not B anymore, we have a C, but transposed. Theoretically, it's extremely interesting because this concept came from an interesting, this concept, this procedure come from a concept, better to say, which is the concept of the duality. An observer or the observability is the dual concept of the controllability in the sense of place eigenvalues. And the dual is a little bit, let me say, complicated in the sense to express now or to explain without helps of equation and so on. But how possible to say in general? I don't know if you remember the eigenvalue of a matrix A or the matrix M are the same of the eigenvalue of the matrix transposed. I don't know if you remember this property. If you don't remember, nothing. This means also this position here is not something which isn't a problem in this sense. This here a little bit more complicated because B and C theoretically two different, let me say, two different matrices, if you want, no? But both at the map in the context of controllability is the map of the input which control the system. In the context of an observer is the map of the signal, let me say, which also control the system because it's something related to a feedback. You remember this matrix B realize the feedback of the state feedback, the state space feedback. Here is quite similar in this sense. And without going in depth on the duality. But again, the eigenvalue of the matrix M equal to the eigenvalue of the matrix M transposed. I don't know if you remember this. This in terms of dynamics, M or the M transpose, they are the same. What here really change is this C instead of B. Why is transposed? Yeah, it's transposed for, let me say, for the technical reasons, because, yeah, we use the same function place, which is, let me say, built for the controllability, but not only. We have, because of the feedback and the duality between A and A transposed, this is easy, or the AD and AD transposed, between B and C transposed, and the results is not in a row as before, but in a column. This means the duality somehow means that what we have an input, now we have an output, let me say, in terms of measurements transposed. And the results before was in a row, now is in a column, and in accordance if I have just one input, of course. This is the two desired lambda 1 and lambda 2, which we have seen also last time we can calculate. No? We have 2 instead of 1, but no problems. And here's a little bit exactly more in depth on the function place, which solves the linear system associated to the following control problem. Now, in the linear system, because also in our case, as before, as last time, where is? As I told you before, this is a linear system, an algebraic linear system, in which the unknown are L21, LN2, L11, no? L21 and L11, or L11, L21. If the system is observable, we are always in a solution. Please calculate K for the system here. Now, as I told you, the eigenvalue of M, the matrix M, equals the eigenvalue of the M transpose. This means the eigenvalue of A minus BK equals the eigenvalue of A minus BK transposed, but because of this. No? But if I apply now the transposition here, we have this eigenvalue of A minus BK equals the eigenvalue of A transposed. Now we can understand a little bit where this rule comes from. Minus K transpose multiply B transpose. We can see here, huh? Because I have to invert when I distribute the transposition. In this sense, we can sketch a little bit that if I change A transposed, if I change instead of A transposed, if I change instead of B, C transposed, if I change instead of K, L transposed, I can use the function place. Because for controller, we used this. Again, this correspondence, which is reflected here, came from a more complex duality between observability and controllability, which I don't have time to calculate, to express. But anyway, A for a controller corresponds to A transpose to an observer. B for a controller corresponds to C transpose for an observer. The matrix K, state space, feedback matrix, do you remember? I told a lot, correspond to L transposed in an observer. Can be seen also with this function place, but really the function space reflects this concept. I don't have time exactly to tell you about this duality. Okay, let me stop here. Let me take a rest again. Let me say 20 minutes, quarter 45. I will come back and we will do an exercise. We will repeat a little bit this part and then we completed the program. Believe me. An exercise with MatraSimulate. Again, 20 minutes, more or less, 45. We take a little bit, and then we have time. Today, I told you I will continue a little bit, but once we discuss together the exercise, we have everything in the hand. Next week, I'm not here, but I will send you all material and the projects. And then the last meeting we discussed, I will go in depth on some aspect which I didn't tell you. It could be that I will tell you about Kalman filter very shortly outside of the program, and then we will discuss. uh, I would like to say if you have questions, otherwise I can scroll down if you don't have question to discuss a little bit the meaning of of the questions, or how I can answer the question a little bit without giving you the solutions, of course. Again, I already told you, you can work with one student, two students, three students, the group. Four students I don't like, but exceptionally, the ideal group is two students, believe me, because you communicate directly and so on. But anyway, we have time to talk about that. 45. Give me the time a little bit to take a little bit of rest because I started 8 o'clock today in the morning. Okay, let me now consider the implementation of this Lundberger observer. I don't know if probably I forgot to give a name of this observer. The name is Lundberger. Lundberger, I show you what in the slide, the name exactly. Let me share. Is here. Lundberger is a professor, I think in California, but I don't remember which university. Now he's emeritus, of course. Uh, he was yeah the professor or the scientist who conceived this kind of observer with variation and so on. As I told you, the Kalman filter, it could be that I will tell you very quickly after next week a little bit about the Kalman filter, but outside of the program of the examination, of course, because Kalman filter or the Kalman filters need really in a full course. It's also not enough because we have also many variations of it. Um, yeah, let me go in the right folder. Today, tomorrow, I will upload everything in my camp or my campus. The simulation slide in the MPC, this part, theoretical, methodological of a Lundberger observer, and its simulation, which I am trying to implement now. You will have, you will find this folder here, discrete observer. We can see a Lundberger observer, no? Discrete. Uh, I think, yeah, let me open this file. I hope we will work, no? Because it's not, the system is always the same. Don't care about if at the beginning I will considering also the position in large matrices. This means we have also position, the derivative position equals velocity, because here we can see that I considered again current velocity. Why that? Because if I consider the position as a state, if I consider the position, and if I don't measure the position, the system is not observable. It could be that I can show you this because this I told you a little bit. I told you a little bit. I told you a little bit about the observability and the controllability a little bit. In order to understand what I intended. Look here, the DC drive. These two equations are the, let me say, the reduction of these three equations. The difference which we have here is we have in the middle, let me say, this kinematic equation. The derivative of the position equals the velocity. We can see here this column of zero. No? because the position is in this model here is not present in any other equations. This means 0 here, 0 here, 0 here, because this element here is multiplied by phi for the first equation. This element here is multiplied by phi by the second for the second equation. This element here is multiplied by phi for the equation number 3. This means we don't have connections between position and the rest of the system. This means I can reduce because such as model as an observer doesn't bring any information about the position if I don't measure the position, because we don't have this connection. In order to be more concrete, the connection which I need, we can see that the position phi is not connected back with the system. This means if I measure omega, if I measure the current, if I measure velocity, if I measure the current, I cannot have information about phi because phi is not involved in the system. Let me colloquially say so. But if I measure phi, of course I can observe omega, I can observe the current, because phi collects, let me say colloquially again, all information. Okay, phi collects information, but we delay. We have a delay here, we have a delay here, but collects information. But vice versa is not valid. Just a little bit to give a more feeling about the observability. No? The controllability, I consider just a few words because a little bit more in general. It could be that after next week I will tell you about that. But anyway, the concept is quite clear. No? It's quite clear. Of course, I can control everything here because the signal here passing through the system can also reach, let me say this word also, phi, omega, and I. For the observability, a little bit more complex, I don't want to say, but we have to consider what I'm measuring and also the structure of the system. For the controllability, we have the input, which I'm considering, and the structure of the system. Anyway, this just intuitively. Okay, let me come back to MATLAB because now the focus today was the observability. Makes sense that in the sense to speak, but okay. Let me run. But before running, I would like to analyze the system together with you. Again, the system is reduced because, as I told you, we are measuring the current sensor. We can see here. I don't know if I share. Let me see. Through the current sensor, I have to realize this observer, which, even though I have an initial condition which is not exactly the same, I will converge to the state. But of course, as I told you, I am assuming that I know the system perfectly. If I don't know the system perfectly, or if I have some disturbances in the measurement, the observer does not work correctly. But we have, or at least this observer does not work correctly. We have to modify this observer. The possible modification is exactly the Kalman filter. With the Kalman filter, even though I don't know perfectly the model, even though we have the measurements affected by errors, nevertheless, we find a good compromise to get, to estimate in this sense, in the best way, in accordance with the cost function. I don't have time to tell you the state which I don't measure, and also, in the best way, the state which I measure. Why that? Because I'm telling you that the measurements are affected by noise, by error. But it could be that next time I will tell you. Look at this. I am calculating the eigenvalue of my matrix AR. Look what I am doing here now. I am calculating the matrix L, everything in continuous at the beginning. Everything in continuous. LC, controller, because why LC? Yeah, it's not controller because an observer. L is the parameter of the inductance. Be careful. place, do you remember AR transpose, CR transpose, because the place can be used also for continuous. And I place the eigenvalues of the observer look at least 10 times faster than the eigenvalue of the system. It makes sense. Because in order to converge quickly, to, let me say, to the value which I don't know, or the variable which I don't know, the observer must be faster than the system. How much? But theoretically, infinite faster. But of course, infinite faster, we can see that we have some numerical problems. In general, yeah, we have some technical problem to realize an infinite fast observer is let me say is easy to understand. Now, it is the continuous. We don't want to do that. Look at this transpose. You remember I explained this. We discretize. For instance, we can use forward Euler, but if you don't like, you can use the exact transformation. We learned a lot about that. Yeah. Then here for the discrete, but you can change. It's not necessarily this. I use the exact discretization. Of course, the exact discretization has some advantages. The question is why we don't use always this. Yeah, good question. We don't use always this because when we apply directly in microcontroller, we don't have the power which is MATLAB. Because to implement this is more heavy for the calculator to implement the forward Euler. Therefore, forward Euler is very often preferred because very often we have some constraints in what? In TS. Because inside TS, I have to run, for instance, MPC, the observer, some filters, different algorithm to check fault and so on. But the structure now of the L is the same. I consider two eigenvalues. Look, real eigenvalue without oscillation because we are in the right segment of the cycle. Inside the cycle, both. I don't know if you see, is basically in the right segment. They're not negative. In the negative segment, we have oscillations. I told you a little bit. Assuming that I don't want to have oscillations, I want to converge relatively fast. I don't know how fast is this. I can calculate for you if you want. But we did together last time, How is the rising time? Using the rising time, we can guess how fast is working the observer. It could be that somewhere, I don't remember really, I mapped this here. I don't remember. Try to do it. Try to do it. Do you remember last time with this concept S? Do you remember? Z equals 1 minus STS multiplied TS. We calculated the position in Z. Do you remember this? Z equal 1 minus S multiplied TS. Yeah, something like that. It could be that I realized it, but I don't remember. It doesn't matter. The important thing is to understand the concept. Now, transposed here, P here, no problem. C transposed. I try to explain a little bit this concept of the duality, which is reflected in this place. At this moment, this is enough so, no? Because the reason is through C, I have the injection of the signal, an observer. Through B, I have the injection of the input, which is nevertheless a signal. Transposed of the matrix A is not a problem because do you remember the matrix, the eigenvalue of a matrix A is equal to the eigenvalue of the matrix A transposed. And if you think again, let me show you again, this could be nice. It's the duality, basically, that we will simulate. The duality can be explained here relatively well. No? Why that? Because from here to here is clear. Now, in our structure, instead of K, we have L. Instead of B, we have L. C. I don't know if it's clear what I intend. Let me show you again this. But the concept of the placement is there. I have to place the eigenvalue of this expression. Which is equivalent to place the eigenvalue of this expression. Now we can understand a little bit better. This means I have to place the eigenvalue A transposed with respect to C transposed to obtain L transposed. A little bit better, probably. But of course, theoretically, it could be that we can understand better, but as I told you, we are not oriented here in much theoretical part because the concept of duality is a little bit more complex. But anyway, I think intuitively you have seen a little bit. It could be that in your future courses, this intuitive idea can help to understand better also the theory. This LD transposed. Let me now run the software. We can see here on the right part in a few seconds the new data. Yeah, we can see. We have everything which we need. Let me open Simulink. I hope that it works. Why I'm saying so? Because sometimes at the end of the lecture, some student ask me modifications and then I forget. Or it happened from an version Simulink to another one that some modification happened. And but let me see. Let me see. Yeah, I hope now. Here I have, I think, if I remember well, the continuous and the discrete observer because they are quite similar. No? Do you remember? Also to demonstrate the dynamics of the error. Yeah, in fact, we can see. I don't know if it's visible. Ah, no, we have just the discrete, excuse me. In this we have just the discrete. Yeah, in which it is possible to connect, please pay attention here, it's possible to connect with any PI control. It is possible to connect with any PI control. But this moment is not connected. Here we have in a system, our motor, a real motor. I am measuring the current. Let me see. CMR is written CMR is 10. Do you remember the current? I have some noise. Let me throw away the noise because it's not included in the observer, in this observer. Basically, I measure the current. Look, I am comparing with the observed current, and you have two inputs here. The input to the system, which could be also the output of the controller if I cannot connect here. And then it's going here inside. Look at the feedback from here, from here to here. The observer is in a controlled system. Let me look here inside. Here's a vector, no? Voltage, first component of the vector, error. Let me show you what I intend. So we can understand better. Look at this on the lateral camera. You have two inputs, voltage multiplied by the discretization of B, TS multiplied B, you remember, BD the name, and error. We have two inputs in the observer. We can write everything in this form. Now it's useful, this idea. Two inputs. Let me open here. Let me share this. This is really important to share what happens here. We have a AD1, which is the name, if I remember well, of the discretized matrix. I assume that I know perfectly the system. No? If I don't assume, we have to modify the observer. Look here. Now we can understand this form BDLD. BD is in a column, LD is in a column, because in the input we have a vector with two components. The voltage, we will multiply by BD1, and the error, which we multiply by LD. CD1, in this case, an identity matrix, because I would like to look for both. And D is the matrix 2 times 2 with 0. Why that? Because we don't have connection between output, input and output, or output and input, better to say. The number of row of D equals the number of row of CD1. CD1 is the name, no? And the number of columns equals number of columns of B, which B with this. But very, very important to observe the form of this B, which consists of two columns. Okay, let me rinse. The main issue is to look how I can estimate the discrete angular velocity if the initial condition is not equal. Here, the initial condition was 0. Let me show you again. Let me show you again. Because if I don't know anything about the initial condition, in the microcontroller, I have to write 0. No? TS is what I am using. Well, TS, I don't remember, is an M file, the TS. But very relatively small because the motor is relatively fast. Look, 0 initial condition. What about the initial condition of the real system? It's not 0. In order to show you how it works. Let me share. This is the initial condition, of, the parameter of the real system. Here I put 1,1, I have to put 1 because here we can simulate what happens if I have an error in the parameter. But of course, if I have an error in the parameters, the observer does not work correctly. And we have to modify. Kalman filter is a modification, an advancement of this. But look, you have two initial conditions, which is not 0. 1 ampere as the current, which is the equivalent current corresponding to a magnetic field inside. And 100 is clear is the velocity. No? Instead of 0 is 100, I think this is radian per second. Now, let me simulate. And to show you, I hope that this works. Let me run. Let me share. Is I try to compare the real velocity with the estimated or observed, better to say, velocity. Let me see if it's possible to see something. Too long simulation. Let me restart. Oh, I know it should be possible. Why it doesn't work? Oh, 1 second. One second again. I don't know. It's running, but it's something I don't like. Yeah, let me show you. It's running. Should be visible. Yeah, we can see that we see. Let me a little bit smaller. Ah, too small. Let me. Yeah, we can see that we see just one line, but it's not exactly correct because at the beginning you can see that we have an error, no? But at the beginning, the observer does not understand that should work in another that orient the estimation or the observation in another direction. It needs time, but we can see nevertheless that after I don't know a very short time is understand that the right direction is another one. This effect is an effect of a picking effect we need. How I can reduce this? And in particular, why we have this effect in the wrong direction? Yeah, this is sometimes how possible to say depends of many, let me say, of many things. One reason is that we have a system which is non-minimum phase system. Um, this means it's not so easy to, let me say, uh, manage the system here. Of course, reducing the speediness, we can reduce this. Sometimes it's enough to avoid this effect, which is basically an effect not so nice to have in the wrong direction of the estimation. Not only the high peak, but also the wrong direction. This is it depends on many reasons. One of them is that if you consider the transfer function uh, uh, between in our system between current, because the current is somehow is our input, state input in the observer, and omega, we have a zero in the real part of a positive. I don't know if I have here somewhere this analysis, but this could be a reason. But what I would like to show you, I can try eventually to show. Before showing this transfer function, let me try to let me share to reduce the speediness. In any case, we will reduce the peak, but it could happen that I can also invert this effect. Let me write 0.9. Do you remember I told you that's close to to 1, we have in the slowest dynamics. Do you remember? one corresponds to s equals 0. And not only, even though I put very close, the real distance of the dynamics is relevant because I compressed an semi-line. Semi-line means a line which has a start but don't have the end. This left real axis. Let me consider this. We will see that we reduced. At least we will reduce. Could be that we avoid also this effect. Let me show you what I intend. Okay, let me run. Okay, let me share. I am sure in any case we reduce. It could be that is not enough to avoid the inversion. In fact, look. Look. But if I reduce, we can also avoid this non-minimum phase effect. About the non-minimum phase, I would like to tell you something in 1 second. Let me reduce again. This means let me write something like that. You remember the map is in a particular map. This distance dynamically is relevant. Oh, what happens? Ah, okay. Let me now change here and let me run. Let me stop the simulations. In any case, we need just the beginning, therefore. Look, you have very small minimum effect. Of course, nevertheless, I have an estimation which converges, of course, but is slow or slower in the convergence. Let me reduce again. And then we will analyze together this effect in another context. Peaking effect. In this case, is not so nice because it's a peaking connected with a non-minimum phase. This means, let me write here. It seems to be two dynamics very close, but there's not. I mean, I can also, in terms of continuous dynamic, to quantify this, also in terms of discrete, but just I would like to remain in the conceptual part. To do a quantization, how we can do. You remember? Let me show you this. You have to for instance, consider the corresponding time constants. You have two time constants. We realize that they're not very close as close the poles in Z. Z, we have Z1 and Z2 really extremely close. I don't remember 10 up to -5, 4, or the 5, something like that. It doesn't matter. You can check. But the time constant is not so close. We can use the idea of last time to calculate S. Even though at this time I did with the exact transformation, or we can do nevertheless with the exact transformation. It's just an exponential. This means we can do in the logarithmic form. Let me run. Yeah, we don't have now. Now, of course, I put an exaggeration. I put an exaggeration. Any uh, non-minimum phase effect. But of course, the convergence is quite slow, no? Even though I stopped relatively early, but we will converge, believe me. Of course, this is an exaggeration to show you nevertheless it's possible. Zero, 1 second. I think we can stop in order to convince you that it is possible. Of course, yeah, we can see that it's slow, but we can see here, if I continue, now we have a 0.4 seconds. This means really less than a half second. But we can see that we don't have this effect. A few words about this effect, if I am able to do this quickly. Let me see. Um, Now we understood how we can move. If I ask something about to fix some dynamics, if we understood in accordance what I told you last time. You can also map directly with the exponential function. What I intend is this one. I will upload everything. No, don't. Yeah. You remember the map which I did today quickly? It's a shame, but nevertheless enough to answer an easy question. This is exactly the map which can be written this form. No? Math, you are better than me in math, I'm sure. And then, of course, I can calculate S with the logarithm from here. S, you remember last time, is connected with the time constant. You know? Do you remember if I have the poles, one divided the poles is lambda, let me say in absolute value. The real part, because of this here. Remember the solution in a differential equation. Then you remember I will consider phi times, same times. If you consider rising time. If I consider just, yeah, if I want to estimate tau 1 and tau 2 in order to see uh, how is the difference, this is enough to calculate S and to do 1 divided S in absolute value. Okay, let me now conclude. Let me see if quickly I can do it for you. I had somehow this example somewhere, but let me see here. Now the problem is I don't remember the. Okay, let me try. It could be that it is easy to show you at the beginning continuous, and then I leave you an exercise at home for discrete, because let me say in continuous. In continuous, we have the matrix A ops, which is equals, do you remember? AR or the AR, no? AR. AR minus L, I think is LC, no? L continuous. Exactly. LC, exactly, which multiply C or the CR. I don't remember. CR probably. CMR. CMR. Let me see how looks like this. This is the matrix. Mhm. I hope no mistakes. Now, look what I can do. Let me write the transfer function, if I remember well the command, or this command at least, of this A or B with respect now to CMR transposed. Then I have a DMR, if I remember well. Let me see. DR, DR. No, BMR, I forgot BR, no? So now, excuse me. Let me see if I understand what I intend. I need, let me see, help transfer function. Okay, I have to define sys. Okay, I have to use numerator denominator. Okay, let me see. This means num then of what? SS2TF. I am trying to calculate the transfer function of the observer. Please look at, uh, let me close this one. Help SS2TF, basically from state space to transfer function, in order to analyze this effect, what is the goal of the non-minimum phase. BR, I think was, as I remember well. CMR, let me see. And DR, let me see. DR. Okay, let me see what happens. I have an error, let me see. I forgot in a parenthesis. Ah, okay, probably here. Something like that. Ah, here, clear, excuse me. Let me see now if I understand what I intend. Another error, let me see. Okay, yeah, I understand. Let me see CMR. Let me see DR. BR. Uh, this says, seems to be correct in my opinion. Matrix C and D must have the same number of rows. Ah, okay, clear, clear, clear. Zero. Correct. Now, in our case, now it works. No? In our case, the output is the velocity. Hmm? Let me say format long. Mm. Uh, let me see where the AUB is correct, I think. Mhm. And here I have to put this. Okay, I didn't see any difference. No, no, no. Um, I don't remember now. Is this one? No? Let me see. Yeah. Mm, don't remember now how we can do that. I will think about. Next week I will try to when things the last Let me see. Could be this is the problem. Let me see. No, this is totally wrong. Clearly. Okay, I will think about how we can show you this not minimum phase effect. And I will tell you as in a particular form and in particular uh, analysis next week. Let me see if I find a better way to show you this non-minimum phase, which we can see that the numerator of the transfer function related to the observer consists of a zero positive. Anyway, let me look at MATLAB. Nevertheless, the course is basically finished, concluded. But of course, after next week, we will fix some aspect, and for the past, we will fix also this aspect here. In the meantime, I will send you the project questions before Tuesday. You will receive everything per email, all material, and also this project. We will discuss after next week, but going a little bit more in depth on what I already told you. What I have to say? Yeah, this is probably I forgot to say something, but I don't remember. I will fix this aspect here together with some points which during the semester I a little bit sketch out in this sense, or the flesh out. Yeah, we will see in 2 weeks. Basically, next week I am not present because I'm traveling, but I will send you the material so you can start also working. Why not on the project? The last lecture is after next week. I hope it was not so boring, but we did a lot of things. We did a lot of things. Next time I will tell you very quickly about, before going ahead, we fix this part, other parts, we discuss the projects. In the project, we will not include the Kalman filter because I will tell you after formulating the projects or questions, let me say. But I would like to tell you a little bit fleshing out what is the idea because it's extremely important. Why is important? Because we cannot know perfectly the system. We cannot know perfectly the parameter of the system, even though we can estimate, we can update. But anyway, the Kalman filter is an alternative form or can combine also adaptively its behavior to estimate what we don't know and to estimate state, even though we have something which we don't know. Now, with this observer, we have seen that we can estimate just the error at the beginning, the initial condition. If you put some uncertainties, it estimates, but we have a bias, try to do it. No? Put a 1,1 in the B matrix in the system. We will see that we have a little bit in the bias. To avoid this bias, to get the mean value, even though we have oscillation, of course, but nevertheless, we get the mean value correctly, even though I don't know the parameters. It's an advantage. This is an advanced observer. Kalman filter one of them, not the unique one. Okay, I will fix some aspect also this at the end. Now I am a little bit tired too. As I told you, I start at 8 o'clock. Thank you really for your participation. Next week I am not here, but in any case, I will communicate everything per email and I will upload in our electronic campus, let me say so. And so we have the material and we can start basically immediately. The last lecture is a little bit in a recap, isn't a lecture nevertheless. And we will see what we can do together, answer questions. It's make a good program to have in advance So we have another meeting, but in any case, you can meet me anytime, also during the examination phase. If I don't answer, please mail again. Write in the object of the mail, question on project, something like that. But it could be there have so many mails. If I am not able to answer, and then it could be that I cannot find anymore. This means don't worry if I don't answer within 24 hours. Mail me again. If you have a question, I'm here for you. Otherwise, we can conclude here.